Yeah, there's extra seats now. For which values of mu s will this system below not move? So we're looking for, in this problem, what two forces are outside the system? Gravity of all of the boxes. So mainly the 3.2. Technically, there's the gravity of this one as well. I'm going to draw a bigger arrow. But that gravity has something that's matching it. What is that? The normal force. We technically have a tension here and a tension there. What are we pulling against, though? We know that this whole unit is about friction. And so we have this table, and we're worried about friction now. And we know that because we're looking for mu s. If it's not moving, what do we start off with? Free points. What do we start off with? F equals ma. And we know that that acceleration is 0. And therefore, the net force is 0 newtons. We also can use our diagram to talk about the net force of the whole system. What is the net force of the whole system equal to? What versus what? Okay, so m2g is the force of gravity, right? Force of gravity equals m2g. And then we have on this side the force of friction. Sorry, I just realized like all these arrows we drew weren't labeled, so I went ahead and labeled them. I flew through that. But we've got m2g, and then we've got the force of friction of box 1, right? Break down the force of friction of box 1. Mu times force normal. What's force normal equal to? You told me, yeah, force gravity of, yeah. So m1g. So m2g minus m1g equals 0, right? We said it's not moving. That's what we started off with, that first line up here. So mu m1g equals m2g. Does that make sense logically? Is all of our pulling down of this box balanced out by the friction over here to keep it from moving? Yes, no? Yes. Okay. Wait, this is super easy now. Mu equals what? M2 over M1. Good. Is that it? Do we have M2 and M1? Looks like it. 3.2 over 5. So even though we did super complicated things yesterday, are all your problems that hard? So what's our answer? 0.64 units? No units. Good. All right. This problem, a 2 kilogram wood block is attached to 0.5 kilogram mass by a string passing through a frictionless pulley. The only thing that this statement helps us with is the frictionless pulley. The pulley doesn't change anything. Is this the same picture? Same idea? Same thing going on? When by the end of all of me showing my work, I'm going to get mu equals m2 over m1 because all my work is the same, that my net force equals ma, that it's not moving, that my system is based off of the force of gravity of that one versus friction of that one. M2G minus force friction of box 1. That my friction is equal to mu times force normal. That my mu times force normal is equal to that box's gravity. M1G. Right? we're on pretty equal footing. The reason why we're doing all of this is to get not the force of the system. We know that's 0, right? We know that's 0. What are we trying to get? The coefficient. Yeah. I like it. 0.5 over 2 equals 0.25. That's the mu value, right? Hey, look, they give us the answer. This is where we said that the key is kind of technically wrong. Right there. Okay, part B. So I want to go over this because all of the work shown in the guide, if you look up the notes on Canvas, they're wrong too. If the same plane surface is now at a 20-degree incline to the horizontal, what minimum mass attached to the string will just get the block to move? What we're doing is we're saying this hanging mass that only has a string on it, what happens, what could we replace it with if we've got a 20-degree slope for the mass on the plane? So I know that's probably greater than 20 degrees, but that's supposed to be my 20-degree incline. It goes over a pulley. That pulley helps change its direction to down. We don't know what M2 is. That's what we're looking for. We have the mass that's on the, what was this, 2 kilograms? I know the phrasing is wrong. Attached to the string. They're both attached to the string, Mr. Kwan. Which mass are we replacing? I'm letting you know right now. I want the mass that's only on the string, not the mass that's on the string and on the inclined plane. What kind of forces are opposed to each other, left, right, on this inclined plane? Do we have anything pulling this down the ramp? Yes. What is it? So gravity goes straight down. This is mg. And then there's some portion of that that goes down the face of the ramp. Because what else is happening to it? We have a, force normal going that way. And so we have, this is mg sine theta. We also need to label force normal as, probably a good idea to label as mg cosine theta. We're going to use that because we're talking about, what topic is this unit over again? Friction. So it's kind of nice to have force normal pre-labeled as mg cosine theta because friction will now be mu mg cosine theta, right? Doesn't that make sense? Because it's going to be mu force normal. Right. So this friction that we have, that we're going to label. Here is where... wait. No, this isn't where. What else? What other forces are outside the system? Or the pair is outside the system, so it's imbalanced. Force gravity of this one. So M2G. I snuck in ones to these. Okay? Because I realized now we have another mass. And I guess, really, what I'm looking at is this box right here that's slipping up or slipping down the ramp. If I want a very tiny mass here, which way are we just barely trying to avoid going? If I have a small mass here, this item will go down the ramp. So which way would friction be if I'm going down the ramp? Up the ramp. What I'm trying to say right now is that friction could pick either side. And so I'm going to do this in a different color. Let's pick green. I'm running out of green ink, but we're going to do it anyway. That this green arrow is my force of friction when friction used to be that way. If I have a heavier mass and I just barely wanted to keep from going up the ramp, I would put my friction to the other side, right? Doesn't that make sense? But friction is that wiggle room of it's neither moving up the ramp nor down the ramp. Well, what's the limit of it? And this one says, what's the smallest mass I could hang here? The smallest mass, this friction has to help that small mass be smaller. If I flip friction to the other side, well, then this pull would get to be greater, right? Doesn't that make sense? I'll say it one more time so you can think through it. This one is currently helping this pull so that this can be smaller to equal out this. This doesn't change. If I want a smaller mass right here, I want it to help. If I flipped friction to the other side, then this mass would be allowed to be bigger, way bigger, right? Because it would work against this. I would need more mass here to oppose it. And I think that's where the notes went wrong online. So if you look it up on Canvas, that's what's going wrong there. When we set up our equation, our net force equals, I'm in the wrong color. Our net force equals MA. Sure. It's a great starter one. And we're not moving, right? Not only are we not moving, we could be moving, but we're definitely not accelerating. What's the other equation? We've got to build this based on our picture. Our net force based on our picture equals what versus what versus what? Three things now. Are you trying to sign? I don't read hand sign. No, it's okay. I'm trying to think of what that is. Oh.
What are you doing?
Aww. Oh, I thought you were like trying to sign F, and I was like, isn't F like, okay. So they're all forces. That's where I was getting confused with. They're all forces. What three forces are in operation up and down the face of the ramp? Friction? Is it negative friction? Which way do you want to be negative? I don't care. Sure. It wants to try to go down the ramp, so we're going to have mg sine theta being our driver force, right? Mg sine theta being our driver force. Down the face of the ramp. So that means negative friction. What did we say that secretly is? Mu mg cosine theta. That's force normal. Mg cosine theta is force normal. Right there. What we're just writing right here is mu force normal. What else is pulling us up the ramp then? M2G. So that's our full system of a problem. Wait, what is our net force equal to? 0. So what do you want to move to the other side with all this? Sure. That's really easy. M2G, because we're looking for M2, right? If we move M2G over, that's awesome. Did I copy it down right? I moved M2G over. Easy next step. What happens next? Cancel out G. So does it matter what planet we're on? Could you imagine me asking that too on a free response, like check the box, which one is it? If we change a planet, what happens? And nothing would happen. It would be the same mass opposed to everything else. All right. M2. These are M1s, by the way, right? M1, M1. That's why we don't move those over. I guess I should probably show my work all the way up with those ones there. Do we have M2? It seems like it. We just need to plug it in. M1 is 2. We don't need G. We need sine. What's the angle? 20? Minus mu. We didn't have that. 0.25 from the previous part. M is 2. Cosine 20. M2 equals that. M2 equals all that jazz.
How do you know that the box will be moving up the slope and not down the slope?
That's a great question. I'm going to answer that by showing you a cool trick in a second. Okay. Okay, because we talked about it. You can review the video. We talked about it for a while, but I'm going to show you another way to justify that in a second. That will help you. What do we get as our answer? 0.214? 0.214 in kilograms. What would we change? What would we mathematically right here change if we were talking about changing the direction of the box and which way friction had to oppose this?
You have to
Plus it. What happens if you put a plus sign there? What do you get? 1.154. So it rounds to 1.2. What does the question ask you? Minimum mass attached to the screen. So our mass is allowed to be within this range and it won't move. Okay? And that's why I think that the problem and the way I solved it in the work on Canvas is wrong, is because this is the valid range of where we haven't met the requirements to move friction-wise. If you have a mass that's too light, then it'll go down this ramp. Once we get to this mass of 0.214, it will stay still. As we increase this mass, increase this mass, increase this mass, it will stay still until we reach 1.15. And once we reach 1.15, this mass is now heavy enough to start pulling down now. Instead of getting pulled up, it will pull down, and this mass will move up the ramp because this is too heavy. But it asks you for the minimum mass. And so within that range, now it makes more sense when we walk through it and have the actual values of what this range could be. This is too light. It would go down this way. Friction would act up the ramp. That's what we were saying, because it helps how this mass would be. That's what we said at the beginning. When this becomes too heavy, this falls down, this slides up the ramp, friction would have flipped to the other side. We would actually move the green arrow to be green arrow. I feel like that's a character. But yeah, we would flip that friction to the other side. Comic books aside. All right.